the volume is the number of moles times what we call the molar volume. This B has units over here of liters per mole, and so that's how much, that's the actual volume that the gas particles themselves occupy. So 1 mole of a gas, that those particles occupy a very small volume. If you look here, um, helium, right? If we convert this to milliliters, for example, it'd be 23.7 milliliters per mole. And that should sound reasonable to you. If we think about water, water is 18 grams per mole, and the density of water is 1 gram per milliliter. And so 1 mole of water is 18 milliliters. And so these are, sort of on the same order of magnitude, the same scale as, a mole of water or something like that. Okay. All right. So using this ideal gas law, again, this is the problem that we worked out at the tail end of class on Friday. And let me take a look at this. We're going to plug it in. For the ideal gas equation, again, I'm going to believe that you can plug that in for yourself. You get 17.7 atmospheres. For the van der Waals equation, the pressure is what we're solving for. We have to add in this A, which is 4.17 atmosphere liter squared per mole squared, times N squared. We had 3.5 moles squared, divided by the volume squared, 5.2 liters squared, times the volume piece, so the volume, 5.2 liters, minus the number of moles, 3.5 moles, times B, 0.0371 liters per mole. And all that is equal to nRT, 3.5 moles, times R, our constant 0.821. My units aren't going to fit here, even though I really want them to. Liters atmospheres per mole Kelvin times the temperature, 47 C, that has to be in Kelvin. We add 273, and we get 320 Kelvin. Okay. So let's do a little bit of algebra. The right side is easy. 3.5 times 0.0821 times 320. This side is 91.95. Now my units, Kelvin cancel, moles cancel, so I'm left with liters times atmospheres. The volume piece, I'm going to do this a little separately. 5.2 minus 3.5 times 0.0371 is 5.07 liters. And then the pressure plus. Lots of times students forget to square these numbers, right? They'll think about just squaring the units, but they won't actually square the value. So don't forget to square your volume and your number of moles. So 4.17 times 3.5 squared divided by 5.2 squared. And we're going to subtract that from P. Well, P plus 1.889 atmospheres.
Dr. Davis,
Yes.
did you get the 17.7 ATM from the chart?
No, that's using the ideal gas equation. So if we just plug in the number of moles, the volume, and the temperature into the regular PV equals nRT, we get.
Oh, okay.
Yeah.
Just threw me off.
It's okay. So 91.95 divided by 5.07 And then we're going to subtract 1.889. We end up with a pressure of 16.2 atmospheres. So this pressure is a little bit smaller than what the ideal gas equation would say. And so since that pressure is smaller, does that mean that the that attractive forces are stronger, or that the repulsive forces are stronger when we talk about it being a real gas?
Attractive.
Right. So let me back up a minute. If we look here, since our pressure is in the top and we're below what we are for ideal gas, Rosie's absolutely right. Attractive forces are what are what bring the most to the table. They're the most important piece. We're not quite high enough pressure where the fact that the gases actually have volume is really affecting us too much. We're in the point where it dips below a little bit, right? So maybe we're around here, where it has dipped below 1, but it hasn't quite gone up yet. Okay. All right. So that's the end of chapter 5.
Dr. Davis,
Guess what? Caroline, question?
what was the final answer on this one again? It's like blocking on my screen.
Sorry, 16.2 atmospheres for the van der Waals equation, for the real gas equation, 17.7 for the ideal gas.
All right, thank you.
All right. So let me change gears here. We're going to switch over to chapter 6. Chapter 6 deals with thermochemistry. So talking about energy and its relationship to chemical reactions. A big part of what we think about, especially for things like physical chemistry and associated topics. So energy, what is energy? This is going to sound a little bit like a physics class here at the beginning, but it's the ability to do work, right? How much work can a system do? That's the energy of that system. Now there are all kinds of different energies out there. What are some varieties of energy?
Kinetic
energy,
Kinetic energy, yeah. So the energy of motion. What else?
potential energy,
Potential energy.
Potential energy, yeah. The energy of position. Sometimes when we talk about kinetic energy, we'll talk about it as thermal energy, right? We equate the motion of molecules with the temperature of those molecules, and so we don't think about that at the grand scale, right? Kinetic energy of a car being equal to its thermal energy, but at the atomic scale, thermal energy and kinetic energy are very closely related. What else? What are some other varieties? What might you have on the top of your house?
Solar.
electrical.
Yeah, solar panels. And so when we think about solar, what we're really talking about is what's called radiant energy, right? Or energy that's in light.
What about is mechanical energy? Like this?
Now, mechanical energy is often a combination of kinetic and potential. You think about the mechanical energy of a spring or something, that spring is loaded and ready to go, and so that's potential energy. So sort of these two together or what we think of when we think of mechanical energy.
Thank you.
Yeah, sure. What's another maybe a little controversial form of energy?
Radioactive.
Nuclear.
Nuclear energy. And of course, the one that we're going to talk about, the one that we don't necessarily think of all the time, chemical energy. Right? And so the difference between nuclear energy and chemical energy, this is the energy that's stored in nuclei. It takes an awful lot of energy to hold all those positive charges that close together. And when something goes wrong, there's a lot of energy that comes out of that nucleus.
Sure, no.
There you go. Chemical energy, however, is stored in chemical bonds. So when you're, burning wood in your fireplace, what you're doing is you're disrupting the chemical bonds that are in the lignin and the cellulose and all the cell walls that are in that wood, and you're converting those. You're breaking those bonds down to the atomic level, so that all you have is carbon and oxygen and hydrogen, and then you're reforming as water and CO2. And so essentially, while there is some chemical energy that you have to put in to form water and CO2, you get out a whole lot more energy from the fire, from the wood, than you put into the water and CO2. And so we're going to talk a lot about heat and work in this chapter. And so thermal energy is what we think of when we think of heat, right? And so heat is related to temperature, but heat is always this movement of energy, right? So this transfer of energy, this movement of energy, right? Temperature, on the other hand, is how we measure thermal energy. Right? We can't measure heat directly. It's not something that we can do because it's that transfer. We can measure a temperature before and a temperature after, and we can say, well, the thermal energy changed this much, and so there must have been that much heat. But we can't actually measure heat directly. Heat's not a quantity that we can measure. And so what we measure is temperature. Right? What I want to get across is that temperature and heat are not the same thing. When you feel a hot fireplace, what you're feeling is that thermal energy being transferred from whatever chemical reactions happening during combustion to your hand, right? You're not actually feeling the temperature increase you feel is the heat transfer, right? And so we need to start separating out those two components. They're very closely related, but they're not the same thing. We need to sort of get through a couple of definitions here, and so these first few slides are a little bit dry, and I apologize. But the next topic that we need to think about is when we're talking about these systems, when we're talking about transfer, what exactly is transferring? Where's it going to? Where's it coming from? And so in thermodynamics, we talk about that as a system, right? And so when we're going to look at systems and different classes of systems, and essentially for us, there are only two things that exist in the universe: whatever we're interested in, and literally everything else, right? And so the system is the actual, chemical reaction that we're looking at, the actual heat transfer activity that we're looking at. The universe is not only, so let's say, for example, that we're doing a reaction in a water-based solution, right? The system is the actual molecules reacting, the solute. Everything else, the solvent, the beaker that it's in, the bench top that it's in, the air around the bench top, you, the building, the elevator, the trees outside, the grass, everything else is the universe. Right? Now, hopefully, if you're doing it right, the chemical reaction that you do in a beaker will not affect the trees outside a whole lot, right? As long as we don't have another Chernobyl. But they're still considered part of that universe. Okay? And so when we have a system could interact with its surroundings, the rest of the universe, in 3 different ways. Okay? In this first way, we call this an open system. And as you can see, there's plenty of heat transfer in and out. And there's also mass transfer. So we have mass transfer with the water vapor going in and out. We also have energy transfer with the heat being able to go in and out. And so this is when you have a steaming cup of coffee, right? You see the steam rise off of it. That's mass leaving. You feel the warmth in your hand. That's the energy transfer. This second system, well, we just add a stopper, so we're going to call it a closed system. So we don't have mass transfer anymore, but we still have energy transfer. Let me put an X here. I'm going to check there so we know. We don't have any mass transfer, but we do have heat transfer. I like to think about this as, the water bottle that you leave in your car overnight. If it's in the summertime, heat's going to get in that water bottle, but no water vapor can leave it. And so it puffs up, it gets very stiff, and when you open the cap, even though it's not carbonated, it goes, right, releases a little bit of pressure. Controversially, if you put it, this weekend, maybe you put your water bottle in your car and you came out the next morning and it was 47 degrees and your water bottle had shriveled up a little bit overnight. Again, the temperature went down, the heat left, so the pressure went down inside the bottle, but no air could get in because it was a closed system. Right. This last one, it's hard to tell on this slide, but this is some insulation. Right, think about it as it's sort of like a thermos. Okay. And we call this an isolated system. He has no heat transfer, he has no mass transfer, he doesn't interact with the surroundings at all. Right? So there's no communication between the system and the surroundings. Now this is, in all honesty, a very difficult and maybe some would say impossible thing to do. We can't have a system that's 100% isolated from the surroundings. But there are very good approximations. I mean, I have a thermos that will keep your ice cold for 24 hours and you'll still have ice. And so they get pretty good, and in the lab they're even better than that. Okay, so these 3 types of systems all differ by whether or not they have energy transfer and whether or not they have mass transfer. So when we are talking about that energy transfer, we can talk about energy leaving the system, like in burning a fire in my fireplace, or energy going into a system. Right? And so in an exothermic process, exo meaning out, right? In an exothermic process, any reaction that gives off heat. And so the system, if we think about this, what's going to happen to the system? Does the temperature of the system go up or go down if the reaction gives off heat?
It goes down.
That's right. The temperature of the system goes down. The surroundings, right, that's everything else in our universe. The temperature goes up. So again, when you're standing in front of the fire, you're part of the surroundings. I hope you're not burning yourself. And so your temperature goes up when you're around the fire, but actually the energy, the temperature of the wood itself is going down, even though that's hard to believe. Okay. For an endothermic process, right, endo meaning in, right, heat has to be applied, right? We have to add heat to the system from the surroundings. I'm going to give the example of fire here. But a good example of an endothermic process that we're all familiar with would be melting ice. Right? If you hold a piece of ice in your hand, the ice takes energy in from your hand, from the surroundings, right? And the temperature of the ice increases and it melts. Right? So the temperature goes up for the system, it goes down for the surroundings. Okay? So that's just the opposite. Endothermic and exothermic. All right. So thermodynamics versus thermochemistry. Thermochemistry, we're looking at specifically chemical reactions and the energy associated with those. Thermodynamics is a little bit broader. It looks at the energy associated with all change, right? Thermo is energy, really thermal energy, so we're talking about heat, but dynamics is change. Okay. Delta U is the energy of the is called the internal energy. And so that's all the energy that the system has, whether it's thermal, whether it's potential, whether it's chemical, whether it's nuclear, all the energy that a system has or the surroundings have is the internal energy. Now, the first law tells us that we can't create energy, we can't destroy energy, we can only transfer it. And so any change we have in the system plus any change we have in the surroundings has to equal 0. So we can't add any, so it can't be positive. We can't destroy any, so it can't be negative. But those changes have to add up to 0. If we rearrange that equation, we get that the internal energy change of the system is equal to the negative of the internal energy change of the surroundings. Do we all know that this little delta means change? So no energy can be made or destroyed. So any energy lost by the system has to be gained by the surroundings, vice versa. Any energy gained by the system has to be lost by the surroundings. And so in this little diagram here, right, in this little photo, there's energy that's lost via combustion. Is that the system or the surroundings that's losing energy?
System.
That's right, system. And so the surroundings must gain exactly the same amount of energy. Now, this is talking about internal energy. So whatever type of energy, that thermal energy could be converted into mechanical energy, right? We could have some kind of steam engine. But whatever it is, the surroundings have to absorb all of that energy that's lost by the system. And so when we think about internal energy, we're going to focus it down to 2 terms. We're going to say that there's heat and that there's work, right? For the moment, we're going to ignore all the other varieties because they're going to be negligible for chemical systems. And we can say that delta U, that internal energy of a system, I'm just going to abbreviate that SYS, is equal to Q plus W. In brackets over here, I'll put heat plus work. Right? So thermal energy and then mechanical energy doing some work, right? So Q for us is heat, W for us is work. When we talk about heat and work, the sign convention, whether it's positive or negative, can get tricky. And so this little table, this is from our textbook. This is table 6.1. From our textbook, talks about how we might write this, how we might see these words, and then what sign that should have when we plug it into our equation. Right? If we say that work was done by the system, right, the system has used up some energy in order to do that work. And so the sign of the change in energy should be negative. Right? And so these first two are work, right? So those are W's. These last two are heat, so that's Q. And so if work is done by the system, the sign of that work should be negative, even if it's not negative in the question. Work done on the system, right? So let's say we're compressing a gas, that we have to do work in order to compress the gas. If you're doing work to compress it, then that energy must be added to the system. And so that's positive. For heat, any heat absorbed by the system in an endothermic process, obviously that's going to be positive. And then any heat lost by the system in an exothermic process, that's going to be negative. Heat's maybe a little bit easier for us to follow than the work. Work done by the system, negative. Work done on the system, positive. Okay. All right. So the work done when a gas is compressed in a cylinder is 462 joules. That's W. During this process, a heat transfer of 128 joules from the gas to surroundings, that's Q. We're going to calculate delta U for this system. Okay. So if it's going from the gas to the surroundings, is that heat transfer Q positive or negative? Did the gas lose it, negative, or gain it, positive?
Lost it.
Positive.
Yeah, it lost it. And so that should be a negative 128 joules, right, for Q. And how about for W? The gas is being compressed. Did the gas lose energy or gain it?
Okay.
Somebody said something.
What's it gain?
Yeah. So it gains 462. I'm going to put plus a positive. I know that's redundant, but just so we're keeping good track of what's positive and what's negative. The 128 joules is lost to the surroundings, and 462 joules is gained via that compression, that work part. Right? Okay. And so we can do this. We get a delta U for this system of 344 joules. 334. Bad math. 334 joules. This is not the first time we've seen a joule, but maybe it's a good time to stop and think about it, right? A joule is an energy unit. Energy is force times distance, and so a Newton meter is a joule. And so we have 1 joule is equal to 1 kilogram meter squared per second squared. We talked through that when we did the gas speed stuff on Friday. Because we live in America, we don't use joules. We don't stick to the SI units. We use calories. Calories are a bit different from a joule. And so 1 calorie is equal to 4.184 joules. We'll come back and talk more about energy. We'll be using joules a lot in this chapter. But I just wanted to give a little refresh, a little intro to it. So, dealing with enthalpy. Up to now, we've been talking about not enthalpy, but internal energy. And so, again, just so we're all on the same page, delta U is a change in internal energy delta H is a change in enthalpy. There's not a huge difference between these two. It just depends on how we measure it. To measure a change in internal energy, well, first off, there's no such thing as an energy meter, right? We can't measure this. We have to measure the heat or the work in order to get internal energy. There's no heat meter, so we look at temperature, right? So we're looking at temperature and we're looking at work to get internal energy. We do the same thing for delta H, enthalpy, but when we look at delta U must be measured at constant volume. This is a very difficult thing for us to do. That would mean that every chemical reaction we ever did would have to be in like a stainless steel box so that the volume can't change at all, right? If we made gas, it's got to stay in there. It can't expand. It's got to stay in that particular volume. And so, a delta U measurement is a very difficult measurement for us to make. Delta H, however, is measured at constant pressure. And it just so happens that we live in a pretty constant pressure world, right? We're at 1 atmosphere, and unless it's a really rainy day or something, then the pressure doesn't change much. And even if it's particularly rainy, it only changes a fraction. But on the time scale of a chemical reaction, a couple of minutes, the pressure in a room doesn't really change. And so delta H is a much easier quantity for us to investigate. And so delta H is equal to Q if we're at a constant pressure. Right? And so it simplifies things for us. We don't have to worry about work anymore. We can focus on the heat part. And it streamlines the way that we can think about energy. When we talk about delta H, right, we're talking about the enthalpy for a chemical reaction. We're talking about the enthalpy for products minus the enthalpy for the reactants. anytime we have a delta, it's always going to be final minus initial, right? And so for delta H, the final state is the products, the initial state is the reactants. And so if we have an exothermic reaction, which has more energy, the reaction, the reactants, or the products?
Reactants.
That's right. If it's exothermic, that means we started with more energy, we gave some away, and our products have less energy. And so if reactants are greater than products, what's the sign of delta H?
Negative.
That's right. I'm just going to put delta H less than 0, right? If it's exothermic. If it's endothermic, of course, the exact opposite is true. We have added energy as we go from reactants to products. And so our products have more energy than the reactants, and our delta H is positive. Okay. Keep these in mind. Okay. Okay. So when we write thermochemical equations, really the only difference between a thermochemical equation and a chemical equation is that we add this little delta H at the end. Okay. And so if we look at the first one, really all it's saying is that the coefficients refer to the number of moles, right? Easy enough. When we think about delta H, it's the energy per mole as written. What does that mean? They haven't given us a great example here, but let's say that I have a reaction 2H2 plus O2 gives me 2H2O. And that's my reaction. Let's say I don't know off the top of my head what delta H is for this, but let's say that it's 600 kilojoules per mole, right? That does not mean that it's 1,200 kilojoules per mole for hydrogen and only 600 kilojoules for oxygen, because there's twice as much hydrogen, right? What that means is that it's 600 kilojoules is released for every 2 moles of hydrogen, or 600 kilojoules is released for every 1 mole of O2, or we could write it for water as well, for every 2 moles of water. I know that's probably squinty and hard to read, but it's per mole as written, and so it's 600 kilojoules no matter which one you're looking at. It's 600 kilojoules for 2 moles of hydrogen, for 1 mole of oxygen, or to make 2 moles of water. Okay. All right, the second piece here, if we reverse the reaction, right, we're just changing reactants and products. The only thing that changes is the sign of our enthalpy. If we start with twice as much and we end up with twice as much, well, we have used twice as much energy. And then the last, and we hopefully got in good practice doing this in chapter 4, when we did all those reactions in aqueous solution, and we had to know if it was a precipitate or aqueous. The states of matter because going from a solid to a liquid doesn't require a whole lot of energy, right? But going from a liquid to a gas requires a huge amount of energy, right? Relatively speaking, it requires 7.5 times as much energy to go from a liquid to a gas as it does from a solid to a gas, from solid to a liquid. And so we need to be mindful of what states we put on our reactions. All right. So let's do a quick example. Given the thermochemical equation below, calculate the heat evolved when 87.9 grams of SO2 is converted to SO3. So we're going to start with that 87 grams of SO2. It gives us the molar mass, the molecular weight here. 1 mole of SO2, 64.07 grams of SO2. Now I need to pull in a conversion factor from my reaction. What's going to go on top?
Two moles.
Grams.
Well, my grams have canceled.
Oh, 2 moles. That's
Joules.
2 moles of SO2 goes on the bottom because I need my moles to cancel. Right? So moles SO2, moles SO2. Then for every 2 moles of SO2, I'm looking for heat, right? I'm looking for energy. How much energy is given off?
Negative 198.2.
Absolutely. Negative 198.2 kilojoules. Right? So this is what I was talking about in the last slide, right? This is kilojoules per mole here. We don't put 396.4 because there's 2 moles of SO2. We just put 198.2. And so we do this, we're left with kilojoules. We do a little bit of math, and we get negative 136 kilojoules.
Dr. Davis.
Yes.
So the only reason that you would ever change or multiply delta H by any factor is if you took that entire equation by that same factor?
Absolutely.
Okay, thank you.
All right, here is another another place where wording gets real tricky for us. Right? The question says, how much heat is evolved? Right? Now, this is not Darwin's version of evolve, but this is given off. Right? How much heat is given off? Well, if it's negative, does that make it endothermic or exothermic?
Exothermic.
Except
That's right. This is exothermic. And so that energy is given off, right? So negative 136 kilojoules tells me that 136 kilojoules was given off. If I say negative 136 kilojoules was given off, that means that it absorbed 136 kilojoules, right? And so this is where wording can get real tricky, right? So 136 kilojoules were evolved. Or think about it as were given off. If it just said, what's the enthalpy change? Negative 136 kilojoules, absolutely. But because it asked for it in that funny wording, we need to make sure we follow what those words mean. Okay. All right, so one more definition, and then we'll do some more examples. When we talk about reactions like this, we're often thinking about how much energy it takes to change the temperature of a substance, right? For example, again, if we're doing a reaction that's in water, we can't measure the energy of that reaction in particular. We can't measure the temperature of those molecules. When we put our thermometer in the water, we're measuring the temperature of the water, more so than the temperature of those molecules. And so we have to know how much energy the water absorbs every degree in order to know how much energy those molecules, that system, has given off. And we call that the specific heat. Right? The specific heat here is the heat required to raise 1 gram of a substance by 1 degree Celsius. Right? And so the units on specific heat, joules per gram degree C. Okay. This is called specific heat in our textbook. Other textbooks use the term specific heat capacity because it's related to heat capacity, right? Heat capacity is the amount of heat required to raise some amount by 1 degree C. And so the units here are just joules per degree C. But the heat capacity changes. If I have 100 grams of water, it's going to be 100 times, so for 100 grams of water, the heat capacity is 418.4 joules per gram, joules per degree C. For a million grams of water, right, C is equal to 4.184 times 10 to the 6th joules per degree C, right? Very different numbers. But the specific heat for water doesn't change, right? S is still 4.184 joules per gram degree C. S down here is still 4.184 joules per gram degree C. And so the specific heat doesn't change, the heat capacity does. And so generally speaking, we use specific heat more often because we don't have to sort of memorize the heat capacity of a particular compound, particular substance. Okay, that's where we will stop. Alex will go through this next example, and I'll just throw this up here for you. Q is equal to the mass times S times delta T. That's how you solve that. Alex goes through that equation, and so if you have any questions, let me know in office hours. Tutorings from 7 to 9 tonight, tomorrow, and Wednesday. And I will see you on Wednesday during office hours.
Thank you very much. Have a fantastic day.
Take care.
Thank you.
Thank you.
Yeah.